Hi y'all, and welcome back to another round of physics. And today, just run a couple of example problems using momentum. I apologize, I've been a little bit behind. It's been a bit trying to keep up with stuff, but I thought, okay, well, I need to run a couple example problems that you can see. And we did these. Some of these we did in class, some of them we didn't complete, and I thought, okay, let's do a complete version of them. So anyway, first up, I thought let's revisit the beta decay, and I gave you a couple extra numbers here, which I think will help out a little bit. And so let's see. During the beta decay, a neutron is converted into a proton and electron. The electron is subsequently ejected from the nucleus at high speed. When a carbon-14 decays into nitrogen-14, the amount of energy released in this process is, and so here's something that differs from class. I actually went through and I actually calculated out the energy that should be released. So here's the energy that would be released. What is the kinetic energy of the ejected electron and the nitrogen atom? Okay. So if you're writing out our chemical formulas, we have something like this. We have 14 and 6, which is carbon, based on the periodic table, goes into 14 and 7 nitrogen plus an electron, E negative. Okay. So this is the process that we're looking at. And for clarification, if you're not familiar, or just to clarify, this top number represents the number of nucleons. That is the number of protons and neutrons found in the nucleus. The bottom number, in some sense, is redundant. This is the number of protons. So knowing the number of protons and the number of nucleons, you can see immediately that in the carbon-14 atom, there's 8 neutrons. Now I say redundant because if you know that it's carbon, you know that it has to have 6 protons right away. Ask a chemist, not me. Now over here, you notice that the number of nucleons stays the same, 14, but the number of protons has increased by 1. In other words, now we have 7 protons and 7 neutrons. So in essence, what has happened here is that 1 neutron has turned into a combination of a proton and an electron. It's decayed into a proton and an electron. So that's physically what's going on here. So now let's see. We have a collision process in reverse. Actually, maybe I shouldn't have erased it, so I'll put it back up here. But you see what we actually have here is a collision process in the reverse. We have a stationary neutron, which ends up turning into a moving proton and a moving electron. So that should hint at us what exactly we want to do here. Okay. So first off, let's do momentum. Okay. And what I'll do is let's go ahead and we'll choose the x-axis to be, something like this. So we'll choose this to be the x-axis, and therefore we have a 1D problem. Okay. So what I'll do here is let's choose the x direction. And we'll go ahead and write everything out. We have the initial momentum of the carbon is equal to the final momentum of the nitrogen plus the final momentum of the electron. Of course, the nice thing is, in the initial problem, carbon initially stationary. In other words, that carbon's just sitting there. And so over here, we'll just substitute in 0. If it's stationary, that means it's not moving. That means the momentum must be equal to 0. And here we'll plug in our definition of momentum. We have the mass of the nitrogen times the final speed of the nitrogen minus plus the mass of the electron, the final speed of the electron. Okay. Now, of course, we have, if we stop and ask ourselves, how many unknowns do we have? We've got 2 right here. So we need to figure out another equation that allows us to actually relate, or, well, we need another equation that contains both of these. And that's where we find right here, okay, this energy piece that I've added in now. We know the collision's inelastic. Inelastic. In other words, we know that the change in kinetic energy is not equal to 0. And the question I have for you is, where does the kinetic energy come from? Okay, that energy had to come from somewhere. And it came from the energy released to pull them apart. You see, I have an energy released in here. That energy gets converted into kinetic energy. So what we're going to do is we're going to say, hey, the change in kinetic energy is equal to this. Say, the change in kinetic energy is equal to this value that's been given, this 4.79 e to the negative 31st. So now I have a way of actually getting my second equation. Now, since I'm lazy, I don't want to have to write all that out. I'll just call this E released for the moment. I'll just call it ER, so the released energy. Of course, using the definition of delta, we have 1/2 the mass of the electron, the final speed of the electron, squared, plus 1/2 the mass of the nitrogen atom, the final speed of the nitrogen atom, squared, minus the initial speed of the carbon. And that should all equal this released energy, ER. Hey, Yahtzee! Let's go ahead. Now I've got 2 equations. I've got 2 unknowns. Let's go ahead and sub and solve this sucker. Physics is done. Algebra takes over. I'll use our first equation right here and solve for one of the speeds. Move this to the other side. I'll have mass of the nitrogen, final speed of the nitrogen, divided by mass of the electron, equals the final speed of the electron. And what we're going to do is we're going to put it right into this sucker. Now, before I run out of space, let's go ahead and move that. Put that right there, safely right there. And I'll go ahead and let's clear the table. Raser la table. Oops. Raser la table. Voilà. Et puis, on doit... Voilà. Here we go. Okay, off and rolling. We're going to take this, we're going to substitute it in right here. So what I have the mass of the electron times the quantity mass of the neutron, mass of the nitrogen, final speed of the nitrogen, divided by the mass of the electron. That quantity is squared. I gotta make sure I got the squared. Plus the mass of the nitrogen, the final speed of the nitrogen, squared. And that whole rigmarole is going to equal 2 times the released energy. Go. All right, I'm going to pull the final speed out. Final speed of the nitrogen squared times the quantity mass of the nitrogen squared divided by mass of the electron plus mass of the nitrogen equals 2ER. Cool. Well, I guess we could get like some sort of common denominator, I guess, if we really wanted to. So we have something that says the final speed of the nitrogen is equal to, let's see, this would be 2 times the released energy, okay, times the mass of the electron, divided by the mass of the nitrogen times the mass of the nitrogen plus the mass of the electron. And of course, we square root it at the end. There we go. Of course, hopefully you can see the advantage to expressing it in this way. If we go back now and substitute it in right here, so I'll put another line in, we have something that says put the mass of the nitrogen divided by the mass of the electron times this quantity, 2 times the energy released, mass of the electron, divided by mass of the nitrogen times mass of the nitrogen plus mass of the electron. This is all to the 1/2. That is equal to my final speed of the electron. And you see you have a mass of the nitrogen and a mass of the nitrogen. You have, excuse me, mass of the electron and mass of the electron. So you can do a little bit of cancellation. We should be able to combine in a little bit. In fact, the final answer would be the final speed of the electron is equal to, you can see it already, 2 times the energy released times the mass of the nitrogen, excuse me, sheesh, mass of the electron, mass of the nitrogen, plus mass of the electron. One half. And we're done. Look at this. We've got the two values that we were after. And you can actually see by keeping it in variable form, we can also see why, in terms of variables, you can see why the electron ends up moving a lot faster. You have the mass of the nitrogen here. Whereas for the nitrogen particle, you can see you have the mass of the electron. And in fact, it's even worse, right? You got these two here as well. Pretty cool. Well, we're essentially done with the problem, but no sense in not subbing in the numbers. So let's go ahead and take a look. What do we get? So go ahead and plug this over here. Okay. And we'll get rid of the rest of this. So let's go at it. So let's go ahead. The kinetic energy of the nitrogen is simply 1/2 mass of the nitrogen, final speed of the nitrogen squared. We can go 1/2 mass of the nitrogen. We go, okay, well this is 2 times the released energy, mass of the electron, divided by mass of the nitrogen times mass of the nitrogen plus mass of the electron. Oh, goody, goody. You say, where's the 1/2? Don't forget we're squaring. You say, oh, goody, goody. See, the mass of the nitrogen actually cancels out here. That's convenient. And we're left with something that says 1/2. I'll say 2 times 4.79. It's an ugly 4 if I've ever seen one. Times 10 to the negative 13th. There we go. 9.1 times 10 to the negative 31. Voila. Then we have 1.67 times 10 to the negative 27th plus 9.1 times 10 to the negative 31st. Of course, if you're really lazy, you recognize in the denominator that the second term, this one, is about 1/1000th of the first term. So if you're really lazy, you just ignore that one altogether. You can. Okay. So let's go ahead. You can ballpark it, of course, but I'll pause it. Let's go ahead, get an idea about the answer. And we're back. I got something like equals 5.21, call it 22, just round it, times 10 to the negative 16th joules. So that's the kinetic energy that I got. 10 to the negative 16th joules. That's the kinetic energy I got. To give you an idea, you might be familiar. Chemists, also high energy physicists, we get bored. We don't like writing this times 10 to the 16th, negative 16th. And so it's common practice to use a different unit called the electron volt. And I'll tell you 1 eV is equal to 1.602 times 10 to the negative 19th joules. So if you're more familiar with this unit, this 5.022 in electron volts, should have ran that before, I get something like, this is equal to 3,256 EV. So about 3.2 keV. Say 3.3, excuse me, kilo electron volts, which is nothing to shake a stick at. That's pretty big. Good? Of course, that's the nitrogen. Let's go ahead and get some idea. So we'll go ahead and keep this piece. Let's go ahead and get some idea about the kinetic energy of the electrons. So this is the kinetic energy of the nitrogen. Okay, well, say I got this, Greg. I got this. Okay, well, very good for you. Always awesome. I'll put 3.3 keV here. I say, okay, well, the kinetic energy of the electron is equal to 1/2 mass of the electron, speed final of the electron squared. And again, we play the same song and dance. Mass of the electron times 2 times the energy released, mass of the nitrogen, divided by mass of the electron, mass of the nitrogen, plus mass of the electron. And again, you say, oh, goody, goody, Greg. Those cancel. Oh, I'm sorry, these cancel too. Oh, silly me. And so we end up with a number of I get something like 4.78 times 10 to the negative 13th joules. Let's see, does that make sense? Yes, oh, excuse me. I should be more careful. This is 787 joules. And you notice why I have to be careful. Look at this. Right here, 4.79. If I take that 7 and round the 8, then it looks like all of the kinetic energy went with the electron, which indeed most of it has. Okay, you notice that this is 3 orders of magnitude larger than the kinetic energy of the nitrogen. So this thing is hauling. This thing gets all of the energy. And again, it's because of the mass of the nitrogen being in the numerator. Okay. Of course, if you're interested, if you want to convert this into electron volts, I have, let me look at this, 2.99 mega electron volts. Other words, 2.9 million, right? This is 10 to the 6th. 2.9 million electron volts. That's how much energy the electron has zipping off of this sucker. Okay? Of course, you can see that's how much energy was released practically in the first place. Yeah? Cool. Now, of course, the point that I was trying to raise with you at this point was this is an experimentally determined value right here. You might say, where does that value come from? The short answer is it comes from E equals mc squared. mc squared. Okay. Now, that's beyond the scope of this course, but that's essentially what happens. If you actually consider the mass of the carbon-14 and the mass, excuse me. Oh, wait, what happened? If you consider the mass of the carbon-14 and compare it to the mass of the nitrogen-7, or nitrogen-14 and the mass of the electron, you'll find out that there's a small change in mass. And that change in mass, if you plug it in here, will tell you how much energy is actually released. Okay. So this number is fixed. Every beta decay of a carbon-14 releases this much energy. Now the issue was, if this is how much energy is released, then that means that the kinetic energy of the electron will always be this 4.788 times 10 to the negative 13th joules. And the kinetic energy of the nitrogen will always be this 5 point whatever, dot, 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 times 10 to the negative 16th joules. Every time. Of course, I showed you, and I'll put this up, magic of editing. You see that the kinetic energy of the electron is not fixed. In other words, it doesn't always have this max value, which is kind of weird. Because if we know that this is the amount of energy that's always given off for every beta decay of a carbon-14, and if it only involves these two particles, then these are the two numbers that it has to be. Now this is where Paulie comes in. The same Paulie from Wolfgang Paulie, same Paulie as the Paulie exclusion principle. And he basically says, you know what? I trust momentum conservation and energy conservation so much that the only way to solve this is to add in a third particle. And so he hypothesized the existence of a third particle called the neutrino. And he actually said, hey, you know what? The neutrino has to be small. It has to be relatively massless. And it has to be chargeless. So neutrino, meaning neutral, because we've already accounted for all of the charge, has to be small and massless, otherwise we would have seen it already. And that's pretty much it. Oops, so I should have put the chargeless with the... Okay. And that was in 1930, just based off of this momentum and energy conservation. Of course, fast forward to 1956, I believe it was 1956, was the first experimental observation of the neutrino. So just a little interesting historical lesson for you there. Okay? Well, let me get the next problem queued up. We'll go at it. Hey, okay, welcome back for another fan favorite. And this one I call the fireworks problem. So a firework of mass 10 kilograms is launched into the air at 25 meters per second at 60 degrees. So, okay, so right away, let's go. There's the ground. We're launching a firework this direction at 60 degrees and 25 meters per second. Okay. Think of it going up and coming down. Think. There we go. At the apex, in other words, at max height, it explodes into two pieces of 2 and 10 kilograms. So right here we get an explosion. Yay. While releasing 100 kilojoules of energy. I have no idea if that's a lot or not. If the two pieces are ejected horizontally, what is the distance between them once they hit the ground? So let's see. Actually, I'm going to draw two diagrams here because something physically changes. It's always good to have a couple diagrams sometimes. So something physically changes here, right here at the top. We get a 2, we get an 8. Sorry, those are pretty small actually. 2 and an 8, and they explode. There's an explosion process. And afterwards, say for example, the 8's going to go way out here, and maybe the 2 will drop down right here. So this is where the firework would have landed had it not exploded. And then you get a path for the 2 kilogram piece, and you get a path for the 8 kilogram piece. And the question is, what's the distance between those? I don't know what to call this. I guess I'll call this delta x pieces. That's what we're trying to find. Well, this is a bear of a problem. Take a minute, see if you can work out some of the steps you think you might need. Okay, got it? Here's some steps I think that we're probably going to like to have. So I'll put 1. We should probably find the max height. Find max height. And I'll put in parentheses here. This is 1 or 2D. I guess this would be kinematics. Okay. That's the first piece that I would be interested in, is using kinematics to find the max height. You say, why? Why would we do that? This comes into step 2. I'd say find falling time. And again, we're going to need kinematics here. And the idea is how far these pieces travel, this 2 and 8 kilogram piece, how far they travel depends on how long they're in the air for. So we can use the max height to figure out how long it takes. We'll say max height, H max. But we can also use this to find out how long it takes, T flight. Still wholly in kinematics. Now the other piece of information that we're going to need is that we need to find the final speed of the 2 kilogram mass and the final speed of the 8 kilogram mass. And we recognize that, oh, okay, we have a collision process, so we're going to use momentum. Right, this is another collision process in reverse. And on top of that, we're going to take some energy considerations, knowing that this collision is inelastic. Similar to the other problem, though, we're told that there's 100 kilojoules of energy released. So presumably that 100 kilojoules goes into the kinetic energy. So I'll put delta KE equals 100 kilojoules. So in that sense, it's much like the last problem. Once we have the falling time and the speeds, we can now calculate distances traveled. Okay. We'll call it delta x2. And at that point, we're talking about, maybe I'll probably set this as my 0 point. So then we can find delta x2, how far the smaller piece travels. We could also find what I'll call delta x8. And therefore, we should be able to find the distance between the two pieces. So we'll call that delta x2 and delta x8. Okay. Are you ready to join me on this adventure? Saddle up. Let's go for it. Okay. Well, the first step, we said, okay, find max height. We already talked about we're going to use kinematics for this. So let's go for it. I'm not going to take the time to sit and think about initial and final states. You should already be able to do that, right? Okay, so here's your chance to pause it and do it. Right, here we go. V final squared in the y direction minus V naught in the y direction squared is equal to 2ay delta y. Goody. Now, of course, our final at the peak is 0. Excuse me. And our initial, I'll say it's V naught sine of theta squared. Right? We're given the initial speed of 25 meters per second. We're told that it's at 60 degrees, and that's enough for us to find the speed in the y direction. So I'll just leave it like this for a moment. Equals negative 2g, and I'll call this h max. So unsurprisingly, we have h max is equal to V naught sine of theta, that whole quantity squared, divided by 2g. Of course, if you want a number for it, let's go ahead. We'll plug that into our handy-dandy calculator, making sure that we are actually in the proper units of angle. And we get 25 times sine of 60 squared divided by 2 times 9.8. I get something like h max is 23.9 meters. And just to let you know, I'm going to store that as variable a in my calculator. And I encourage you, this is something that's smart to do, storing it in your calculator. So you can see it. Oh, maybe. Angle. Okay. Woo! Okay. Store it in your calculator. Make a note of what you stored it under. Then you know where it is. So step 2. Falling time. Again, I'll let you have a second. See if you can come up with this. Got it? And there's at least 2 different ways to go at this. I will go for the one that seems to make more sense to me. I'll just say delta y is equal to V naught t plus 1/2 at squared. Of course, okay, well, final, we'll say that my initial is when it's up here at the top. Final is when it hits the ground. So I get negative h max equals 0 minus 1/2 gt squared. And so I get something like 2 times the max height divided by g square rooted equals t. Now, of course, you see I have this expression. So if I really wanted to, you could rewrite this as being, let's see. Oh, that's interesting. Isn't that handy? If I substitute that in, V naught sine of theta squared divided by 2g squared, that whole quantity is square rooted. And of course you see, oh goody goody, the 2's cancel. And then I have everything squared in a square root. This is just V naught sine of theta divided by g. That's equal to my time interval. Of course, plugging in, if you'd prefer, 25 times sine of 60 divided by 9.8. Working on my robot voice. I get something like 2.2, I'll keep the extra decimal, seconds equals t. And I'll go ahead and I'm going to store that as variable b, as in boy. Good so far? Okay. Let's go ahead. Let's, excuse me. So I'm going to go ahead. Let's get rid of some of this. And what we're going to do is, what I am going to do is just shift all of this up. So there's our results from step 1. Step 2 is right here. I'm going to put that right here on this side, and we're just going to store all of this. course, I imagine that you probably have some better way of doing it. That is A-okay with me, as long as you know how to present the information. There we go. So we're on to step 3. In step 3, we're after finding the initial or the final speeds of the 2 and the 8 kilogram mass. And here's where we use the idea that they're projected horizontally. In other words, rather than thinking of these 2D vectors or these 3D vectors, that would be the next example problem, we can just simply think of this as being in the x direction. So we can write the initial is equal to the final. Ta-da! Okay? Of course, initially we have to be careful because now we don't have an object at rest. The firework is arcing over. So even at the peak, it's still moving, horizontally, of course. So here we have mass, the 10 kilogram mass. What should I put down for the speed in the x direction? Because the acceleration is 0 in the x direction, I could write v naught cosine of the launch angle. There is the momentum initially. Of course, finally, I have mass of the 2, just put 2 there, plus mass of the 8, v8. Okay. So I'll just subscript it. I'll drop the final. I'll just leave the 8 or the 2. Okay. That's as far as we can get here right now. We have those 2 rigmaroles. Excuse me, that's supposed to be an underline. It looked like a 3. We have those 2 rigmaroles. And this is where we have to go to our change in kinetic energy. So we're told the change in kinetic energy, it's inelastic, it's not 0. And specifically, we're told how much energy is released in this process, this explosion. Ugh. It's going to get kind of ugly kind of fast, isn't it? Such is life. So we have, if we think about it, we have 1/2 mass of the 2 kilogram v final of the 2 plus 1/2 mass of the 8 times v of the 8 squared minus 1/2 the mass of the 10 times its initial squared. And this will be equal to the energy released. Sorry about that. Okay. Sorry for the phone ringing there in the background. Let's keep going. So now we see, haha, we've got 2 unknowns. We've got 2 equations. You know what's going to happen. We got to sub and solve this sucker. Bugger. Oh, excuse me. I should be a little bit careful here, right? I got flustered. Right here, right, it's not the initial launch speed of 25 meters per second. We still have that cosine squared of theta in here. That's the energy released. Remember, that 10 kilogram mass is moving perfectly horizontally at that point. There's no vertical motion. Okay, so we need that cosine piece. Well, bugger. I think it was Yogi Berra that said the quickest way around is straight through. We have no choice here. Okay, well, let's take this. I'm going to take this and solve for, say, V2. So I have M10 V naught cosine of theta minus M8 V8 divided by M2 equals V2. Now we're going to have to sub it right there in that rigmarole. Oh, a nutser. I'll multiply by 2. So I have M2 times, oh, you know what, before we do that, let's go ahead and I'm going to move this out of the way. So here's one result that I have. Let me move this out of the way. I'll just move it right there. Because this is going to get pretty ugly pretty fast, and so I'm going to want as much space as possible to work this out. Okay. Let me move this over here. Okay. I've avoided it long enough. Okay, now let's go. So we have, I'll say I multiply everything out by 2. So I get M2 times the quantity m10 cosine of theta times v naught, excuse me, I dropped that, minus m8 v8 over m2. That quantity will be squared plus m8 v8 minus m10 v naught squared cosine squared of theta equals 2 times ER. Probably want to go to the ER soon. Oh, goody goody. At least this m2 will cancel this one in the denominator. Okay. And let's go ahead and FOIL the numerator. Wah, wah. Remember, we're trying to get v8 by itself here. Wah, wah. So let's FOIL that sucker. Okay. Well, we got 1 over m2. Not for the faint of heart here. m10 v naught cosine of theta. That quantity is squared indeed. Minus 2 m8 m10 v naught v8 cosine of theta plus m8 squared v8 squared. Dropped a squared there, just be careful. Plus m8 v8 squared minus m10 v naught squared cosine squared of theta equals 2ER. Character builder. Yeah! Well, let's go ahead. Let's get the squared terms by themselves. So I see that I have one squared term here and one there. So I have something that says v8 squared times the quantity m8 plus m8 squared over m2. That's the first term. So I got that guy and this guy. Excuse me. Let's go for the second term, the linear terms, which is right here. And I have something that says minus 2 times m8 m10 v naught cosine theta divided by m2. There we go. So we have times v8. Let's make sure we got everything. 2 m8 m10 v naught cosine of theta m2, and then we have the v8 there. That's it. That takes care of that term. Next, well, we got this rigmarole. We have plus. We've got this piece, m10 v naught cosine of theta, that whole rigmarole squared, divided by m2. I'll put this in a square bracket for a moment. That takes care of this piece right here. We've got that piece minus m10 v naught squared cosine squared of theta. And then we've got this piece minus 2ER equals 0. Now you see why I said, okay, well, let's take a minute and get the space cleared off and that kind of stuff. Now, there are times when it's really good to work in variables. Okay? Right here is where I say, okay, it will no longer serve us to keep working in variables here. Okay? Or at least I'm not going to keep working on these variables that we have. Okay? Please realize you have a number for this, right? 64 divided by 2 plus 8. You have a number for this. You can calculate out the numbers. You have a number for this. Okay? Those are all numbers. So what I'm going to do, I'm going to calculate this out, and I'm going to store it in my calculator. And I'm going to store that one as variable x. Okay? I'm going to do this one. I'm going to store it as y. I'm going to do this one. I'm store it as z. That's a terrible x. So I'm going to get those three numbers, and then we're going to perform the quadratic equation using those three numbers. So go ahead, calculate them out. But for example, you have 8 plus 64 divided by 2. So this rigmarole, 64 divided by 2 is 32, excuse me, plus 8. So this should be 40. So I'm going to store the value of 40 as x. I'll say this is 40, and I'll store that value as x. This next one, well, let's go ahead. Let's go ahead and hack that out. So I have 2 times 8 times 10 times 25 times cosine of 60. And that whole rigmarole is divided by 2. Okay. Well, gee. I must have planned this out rather nicely. I got 1,000 times my variable. So 40 will represent x. I got 1,000 for y. Well, shoot. Yippee-ki-yay. Maybe I'll get lucky on the third one, right? You get 10 times 25 times cosine of 60. That whole quantity is squared, divided by 2. And then you subtract 10 times 25 squared times the cosine of 60 squared, right, minus 2 times 1,000, or excuse me, 2 times 100 times 1,000, right, kilojoules. So there's 100 kilojoules, that's 100 times 1,000. Wow. Cool. So I still end up with a nice round number serendipitously. So even though these look like garbage, I still end up with a nice round number of minus 19,3750 equals 0. So again, I'll call this value x, I'll call this value y, I'll call this one z. Of course, too bad I can't use A, B, and C because you notice I already used A and B earlier. So there we go. There's our quadratic equation that we needed in order to solve. So let's go at it. Of course, V8, I love it. That's 1,000 plus or minus the square root of 1,000 squared minus 4 times A, 40, times C, this huge mess, 19,3750. Of course, you notice that was a negative. Okay. That's to the 1/2, all over 2 times 40. We go at it. Solve that sucker. Beat that wall, beat that wall, beat that wall. Okay, take a minute, hack it out. I'll do it too. We'll be right back. Hey, I got it. Hopefully you did too. I got an answer here of V8. So if I take the plus sign, I get something like 83.2 meters per second. And if I take the minus sign, I get negative 58.2 meters per second. So the real question is, which one of these do I take? And I'll say, I guess we gotta be a little bit careful here, but if I go back and I look at the initial equation for the momentum, okay, you notice I chose positive for both of them. So I was going to inherently end up with a negative sign somewhere. Okay. So which one do we take? This is a very good question. I am going to point out a different issue. Yes. Right here, notice that I solved for V2. I arbitrarily did. And you'll also notice that I would have gotten the exact same equation had I solved for, oh, no. Stop there. So I've got my value for V2, V8. Yep. Let's go ahead. Let's see, what value do I get for V2 if I use this for V8? Okay. So I'm going to use this equation right here. There we go. Let's get an idea. So you get 10 times 25 times cosine of 60 minus the 8 kilogram mass times 83.2. Okay. And divided by 2. What do we get for V2 here? So let's go ahead. Store that as alpha. Incidentally, I'm going to store this as alpha D. I'm going to store this one as alpha E. Just remind myself of that. Alpha D. Oops, excuse me. Go to stores alpha D. There we go. I forgot to store the other one, so I got to go and get it real fast. Stores alpha E. There we go. Perfect. Okay. So now I have 10 times 25 times cosine of 60 minus 8 times alpha D divided by 2. There we go. So I get something that says, hey, V2 is negative 270 meters per second equals V2. The other one is I could use this one. So again, I get 10 times 25 cosine of 60 minus 8 times negative 58.2, all divided by 2. I think we're going to run into something here that'll be interesting. 10 times 25 times cosine of 60, at least I anticipate something interesting, minus 8 times alpha E, ding, divided by 2. Okay, so we get 295.3 meters per second equals V2. And we got it. Okay. So the issue here, we have to know which piece flies which direction, essentially. When we have the explosion, okay, you either have the 2 kilogram piece going this way and the 8 kilogram piece going that way, and in which case, here are your values. On the other hand, rather than the 2 kilogram piece, say that this is the 8-1 going backwards, and this is the 2-1. Keeping in mind, we actually called that direction positive x when we set up our initial equations. And if this is the case, then it's these two values that we should be using. Which is kind of interesting. Okay. So one of the interesting things that I note is that if I look at the relative speed between these two pieces, it ends up being like 353 meters per second. And the same thing, the relative speed between these two pieces, 353 meters per second. So the interesting thing is, this is the speed, the relative speed between them. It doesn't matter which situation you have in terms of how far they're moving with respect to each other. Okay? Well, we're at the home stretch. Bazinga. And now I realize something interesting. If this is the relative speed and we have the time of flight, we can find how far away from each other they land right away. Right? This is the speed. This 353 is the speed of piece 2 with respect to piece 8. So it's thinking of piece 8 as being stationary and piece 2 flying away at 353 meters per second. So we can actually shortcut this last step if we are smart about it. Ready? 353 times 2.21 times alpha b. Done. I get something, since I'm considering the acceleration in the x direction to be 0, I get something like these two pieces land 781 meters apart. Cool. Yeah? Yeah? Okay. Maybe you don't believe me on that. That's fine. You don't have to. Let's go ahead and... So we got an idea about what it is. Let's go ahead and go ahead and let's just do it. Oops, excuse me. Let's go ahead and just do it. Here's the second one. Take that situation, for example. The other one will be just as valid. So we think that's like 781. Let's just do it now. Okay. We have the speed for the first one. V8 times the time will equal how far piece 8 travels. Of course, we're making the assumption the acceleration is equal to 0. So you get something like 83.2 times 2.21 equals delta x of the 8 piece. Okay? So that's what? Alpha d times alpha b. I get 183 meters, 0.8 meters, equals delta x 8. We also have v2t equals delta x of 2. Again, assuming that the acceleration is 0. But here it's negative 270, whopping negative 270 times 2.21. And so I have alpha f times alpha b. A whopping negative 597.2 meters. Delta x2. So in other words, if this is where the explosion has occurred, piece 2 lands 597 meters away, and piece 8 lands at 183.8 meters. So the total distance between these two will be a whopping 781 meters. Of course, you can see now where that came from. Okay. I think I'll stop it there. I'll do one more video about a 2D collision, but right here I think that I've probably taken up enough of your time for today. Thanks for your attention. I'll see you next time.